Neural cell automata is a special type of cell automata where the update rule is modeled by a neural network. We can train these neural networks to perform different tasks, for example, synthesizing texture patterns. This particular neural CA is unable to build a coherent pattern if we disturb the grid state with noise. In this tutorial, we will train a cell automata that is not only robust to high levels of environmental noise, but can also change its behavior depending on this noise level. The idea for today's experiment is inspired by this tweet by Professor Michael Levin. The tweet points to the article that discusses ways multicellular organisms utilize noise to facilitate cell differentiation and importance of utilizing noise in designing synthetic organisms. I decided to try to design a neural cell automata that is sensitive to the environmental noise level and can be controlled by varying this level. I use a Self-Organizing Textures article as a starting point and will build upon the PyTorch version of the accompaniment. I will start by modifying the code a little bit to implement the changes that I came up with when I was preparing the tutorial on neural CAs for the A-Life conference. In particular, it happens that neural cell automata perception works better when I don't normalize Sobel and Laplacian kernels that neural CA uses. Uh, Not sure why is it the case, probably because it facilitates the flow of gradient through the perception channels that exchange information with cell neighbors. And the second change, it happens that cell automata still trains properly when we inject the seed less often into the training batches. So this means that hopefully cell automata is more stable over the longer evaluation runs, because we on each training step we unroll the cell automata execution only for a number of steps from this range, but putting the final states back into the sample pool and getting them back, sampling them for a new batch, we can simulate the evolution of cell automata over much longer sequences of steps. So, and then the third change I want to implement is something that is useful for making sure that cell automata doesn't utilize uh, channel values that are too large, which I think is useful when we are going to inject noise into the system, so that cell automata don't avoid additive noise by just making the values of internal activations larger, but doing something smarter than that. So I'm adding so-called overflow loss. That's just the sum of absolute values of clamped version of grid state and the original version. And I will add this term to overall loss. Now we can pick some pattern. Let's pick those nice bubbles from the DTD dataset. I will replace the URL of the image that I'm using as a target, so it's bubbly 0101. Oops, I didn't run all the cells. And now we should probably be ready to start training. Just a second. Downloads the VGG parameters that we use in texture descriptor function. And yes, now we run training. This time I got lucky, I got P100 GPU, so training is going to take probably a few minutes. Let's make the uh, training loop to display the current batch a little bit more often, so that we see the progress of the cell automata training. So it seems to be training, and while it minimizes the loss, let's modify the definition of our neural cell automata to add additional parameter that controls the noise level of the system. So I just, in case noise level is provided, I'm just adding the normal noise to current input grid state before applying the neural CA rule. I'm also a bit curious about the value of overflow loss that I've just introduced. After a little bit more than 2000 of steps, we got decent bubbles. Let's see what the behavior of this model looks like in dynamics, and let's save the model for future experiments. Wrong parameter order. And the video looks like this. Yeah, looks like a reasonable starting point to begin experiments with noise. Before continuing, I think it's a good moment to actually save a copy of our notebook in Drive, because previously I opened it from GitHub. Let's connect to the kernel again. Oh wow, I've got V100. I will upload the pre-trained checkpoint to the kernel, and let's load it instead of training from scratch. The model seems to work. Now, as we modified our cell automata definition to accept the noise level parameter, let's see what would happen if we start injecting some noise at every iteration. Let's start with some small value. We see that while background is a little bit noisy, our model is reasonably tolerant to noise. Let's increase the level, say let's add 2. At this noise level, the model struggles to produce bubbles. One bubble somehow happened to grow and survive, but all others got destroyed. Now I would like to see what would model behavior look like if I vary the noise level across space. I will vary the noise level across the x-axis of the grid according to this formula. So noise will be maximum in the center and 0 around the boundaries. Okay, looks like we got behavior that varies across the grid. Now let's generate a video. You see that I'm passing the array of noises that gets broadcasted across all other dimensions. So the grid has shape b, which is the number of samples in batch. Uh, it's better to show like this. So this is number of samples in batch, this is number of channels, this is the height of the grid, and this is the width of the grid. So when I pass array of shape of shape 256, this dimension gets matched to the last dimension of the grid state tensor, and all other dimensions got broadcasted. So effectively I'm applying a different noise level for each columns of each channel of each element of a batch. Now we see that there is an area in the middle that is very noisy, and the model struggles to generate patterns there, although patterns seem to persist when they drift into this area. Let's render a bit more frames, or maybe just accelerate the video. Okay, that's interesting. So the model can't generate bubbles in the noisy area, but can persist if pattern enters there. So sometimes it can even cross this dangerous area. Okay, as a first experiment, let's now train a model that would be more persistent to noise. We can do this by injecting noise during model training. We start from loaded checkpoint instead of randomly initialized state. Our model quickly learns to develop patterns in presence of very strong noise, and well, if we wait longer, probably it will match the quality of the original model. Let's see what would the video look like at this stage after 1000 iterations of optimization. We now have a model that performs equally well in high noise area and in area without noise. There are some artifacts which will probably go away if we train longer, or maybe those artifacts actually come from the fact that a now model is trained in a regime with noise only, so it may have forgotten how to build a pattern when noise is not present, and it relies on noise to actually destroy these waves at the background. Noise-robust training is a little bit similar to quantization-aware training of neural network. When the system is trained to operate on a hardware that has low-precision arithmetics by injecting the fake quantization operations into the neural network graph. Today I want to try something different. I want to create a network that behaves differently depending on whether noise is present or not. We can think of this as a network that performs different tasks depending on the arithmetic precision of hardware that it runs on, or a network that behaves differently depending on whether dropout is applied or not. Let's now modify the training loop. We will apply noise only to some samples from a batch, depending on the batch index, which corresponds to a position of a corresponding sample in a sample pool. So for even batch indexes we will train without noise, and for odd we will apply noise. And also we will apply different loss functions for odd and even samples. Now we will load one more image that we'll use as a target texture in presence of noise. I decided to try this checkerboard texture as a target for noisy conditions. we've loaded and computed styles for two different textures, target styles. So now target styles is a list where each element corresponds to a gram matrix computed from a corresponding layer of a pre-trained network. And if we look at shapes of those matrices, then we will, for example, the first element, we will see that now each of those, we have two matrices. Zeros corresponds to first texture and first corresponds to the second texture. And this is true for all elements of this list. We can now individually select different targets for different samples in a training batch. Note that we must do a selection for all gram matrices. So training seems to be going on. We may see this interesting bending in losses for different training batches. Probably the loss happens to be lower for one pattern than for the other, and these four bands correspond to different ratios of pattern 0 and pattern 1 in training batches. But we see that over time, for all of those cases, loss seems to be going down, and we see that there is differentiation, that some samples looks like they're turning into bubbles and some are trying to become a checkerboard. This model took quite a while to train, and still didn't reach the quality of a single pattern model. I suspect that increasing the batch size might have sped up the training, but I think it's okay for now, and I'm eager to try to use this model in our spatially varying noise scenario. Let's also save it. And let's look how will it behave in case of spatially varying noise. Well, as expected, now in low noise area the cell automata produces bubble texture, and in high noise areas it produces checkerboard, and there is some threshold where transition from one pattern to another happens. Let's now try to see what would happen if we vary the noise not only across space but also over time. Now the noise equals to 0 near borders and 0.02 in the middle for the first half of the video, for the first 100 of frames, and then it flips, so it becomes 0 in the center and high noise at the boundaries, and we see that our cell automata reacts to the change properly. Let's see if it can flip one more time. I'll make a longer video. And now we see that we've successfully trained the noise conditioned model which dramatically changes its behavior depending on the environment properties, on the level of noise in the environment. I think another interesting property of the resulting system is that it can dynamically adapt its behavior to changes in the environment noise level. And this is out of training situation because during training each sample was observing a static noise level, either present noise or no noise. And there is no guarantee that if we rerun training we will get the similar behavior, but this time we got lucky. Other variant could be that the system doesn't change the pattern when noise level changes, or that it sticks to one configuration, preferably to another. Say it could have changed from bubbles to chessboard, but not the other way. I hope you enjoyed this little tutorial. I'm going to add links to the final notebook and other related materials into the video description, and looking forward to hearing your feedback. So please leave comments or reach out to me. Let me know if you have ideas where to go next from this little experiment, or if you think that it deserves to become a full-fledged article or distill post. So thank you for your attention.